second ordinary differential equation is going to be solved using the Laplace transform today. So if you've not seen the first video, go and check it out. It came out a few days ago, but today we're looking at another non-homogeneous ordinary differential equation solved with the Laplace transform. Here it is. So the second derivative of f of t minus 2 times the first derivative of f of t plus 10 times f of t equals 10e to the 2t. It's non-homogeneous because it's equal to a function, not 0. So if this was blah 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 equals 0, that would be a homogeneous differential equation. We also get given the boundary conditions that f of 0 is 0 and f prime of 0 is 1. Let's go straight in. So as always, hopefully you guys are pretty comfortable with this so far. Up to now, we're going to be taking Laplace transforms of everything. So we're going to be taking the Laplace transform of the second derivative minus 2 times the Laplace transform of the first derivative plus 10 times the Laplace transform of the original function equals I could say 10 times the Laplace transform of e to the 2t, like this. Now let's actually plug everything in, and I'm going to assume you guys are happy, as I have been doing in this video, the last video. I'm going to assume you guys are happy with what the Laplace transform of everything is. If you're not, link in description to the playlist on Laplace transforms. The first function, the second derivative, becomes s squared, where remember s is our new variable, times f of s, capital F of s that is, minus s times f of 0 minus f prime of 0. That's the first term. Then we've got minus 2 lots of the derivative, which is s times f of s minus the original function at 0, plus 10 times the Laplace transform of f of t is just capital F of s, and this is 10 times the Laplace transform of e to the 2t, which is 1 over s minus 2. So it's 10 over s minus 2 there. Okay, now we're going to do what we typically do first, which is to plug the f of 0 and f prime of 0 values in. So s squared times capital F of s. F of 0 is 0 in this question, so this term is just gone. And f prime of 0 is 1, so minus 1. And then I'm going to expand this out, so minus 2 times s times capital F of s. Remember, f of 0 is 0 again, so that's just ignored. Plus 10 times capital F of s equals 10 over s minus 2, like that. Okay, then what we want to do is factor out the f of s and get everything else on the other side. So I'm going to go f of s, big bracket, s squared minus 2s plus 10 equals 10 over s minus 2. And of course, there's this minus 1 term that was on the left. Let's add 1 to both sides so we can have the plus 1 there. Okay, cool stuff. Now let's divide both sides by s squared minus 2s plus 10. Because remember, guys, the whole point of taking Laplace transforms is to produce an algebraic equation that we can then solve for f of s, and then we'll take the inverse Laplace transform. So doing that, we've got 10 over s minus 2 times s squared minus 2s plus 10 plus 1 over s squared minus 2s plus 10. Okay, cool. Now, guys, what we would like to do for the first one, we're going to treat these separately. We can't directly take the inverse Laplace transform yet because they're not in a nice enough form. It's not obvious what the inverse Laplace transform is, because at the moment, the only tool that we have to find the inverse Laplace transform is to just remember or think about what would Laplace transform to that thing, that function in terms of s. So it's basically just thinking backwards, but right now it's very difficult to think backwards, so we need to make this look nicer. So what you would do is you would put the first term in partial fractions, okay? The first term would go into partial fractions. Now, to avoid the video being extremely long, I'm going to assume that everyone watching this video is pretty happy with partial fractions. If you're not happy with what I'm about to do, because I'm just going to tell you what it is, please leave a comment, and potentially, if enough people want it, I will make an unlisted YouTube video that I'll leave the link to in the description for you guys to check out the algebra. But I'm going to assume everyone's pretty happy, so I'm just going to tell you what this would become if you put it into partial fractions. Okay guys, so I've just done it here. So this first term, 10 over s minus 2 times the quadratic, when you put it into partial fractions, you'll get 1 over s minus 2 plus minus s over s squared minus 2s plus 10. So remember, you're allowed to have a variable. You might say, wait a second, how have you got an s in the numerator? You're allowed to do that if you're dealing with a quadratic term on the denominator. You might notice that the quadratic doesn't factorize. So s squared minus 2s plus 10 does not have any real roots, which means it's not factorizable in the real numbers. So when that happens, you're allowed to say that I'm going to have like a over s minus 2 plus bs plus c over s squared minus 2s plus 10. So you're allowed to assume there is a linear term up here. The constant ends up being 0, and the coefficient of s is minus 1. So you get this. And then 1 over s squared minus 2s plus 10, we're going to complete the square on this one because, again, it can't be factorized. So this isn't partial fractions anymore. This is just a different way of doing this. And we've got s minus 1 squared plus 9 there. All of this is simply for the purpose of allowing us to figure out what that inverse Laplace transform is going to be. So hopefully you guys are pretty happy with this. At the moment, it's just algebra, okay? Now, to make this a bit nicer, what I'm going to do with that middle term here is I'm going to, first of all, I'll leave the minus up there, but I'd also like to complete the square on this one as well. Of course, it's the same thing. And the reason why I'm going to do this is because you might see that the 1 over s minus 2, that's fine. We know what the inverse Laplace transform of that would be. It would be e to the 2t. So there's no issue with that. The other two terms are much harder. However, we can combine them like this. So what we have is, again, 1 over s minus 2. We can just ignore that because that's pretty easy. But then what we've got, and I'm going to write it like this, I'm going to factor the minus out, and then I'm going to combine these two terms to one fraction. So I'm going to go s minus 1 over s minus 1 squared, and I'm also going to turn the number 9 into a 3 squared, and you'll see why it's a bit nicer to do that. Hopefully this makes sense. Again, it's all just algebra so far, but this is the clever bit, guys. I'm going to write down a couple of things. So let's just remind ourselves that the Laplace transform of cosine of 3t is, do we remember what it is? It's s over s squared plus 3 squared. That is the Laplace transform of cos of 3t. I've got a video on this. So if you don't know that, then there's a video. But normally when you do an exam, you're going to have your Laplace transform table. And basically you're going to have this on it. So cos of AT or BT or whatever it says on yours is going to be s over s squared plus a squared, or s over s squared plus b squared, or whatever it is. In my video, I used omega. So the Laplace transform of cos of omega t is s over s squared plus omega squared. Why do I mention this? Well, guys, look at how similar this is compared to this fraction. The only difference between what I've written in yellow and what's in the question in white is, of course, that we've got s minus 1s here. But also remember what we call the first shifting theorem, okay, which says that the Laplace transform of e to the at, that's not written very well, let me try that again, e to the at, that's an e to the at, even though it looks terrible, times a function that is Laplace transformable is equal to the Laplace transform of f of t, but shifted by a. This is the first shifting theorem, okay? Now, what we have is, we have the Laplace transform of cos of 3t, but it is shifted because all of the s's have been replaced by s minus 1s. So, in a second, this is going to come full circle, but if I just take the inverse Laplace transform of both sides, I will have that f of t is equal to the inverse Laplace transform of 1 over s minus 2 minus the inverse Laplace transform of s minus 1 over s minus 1 squared plus 3 squared. Like that. And let me just, because my handwriting's a bit shocking there, that's a squared, looks kind of like a cubed. That's a squared there, lovely. And of course, we can now see what that second one is, the big one. We can see what that is. So f of t is, doing the easy one first, this is just e to the 2t, because again, remember the Laplace transform of e to the 2t is 1 over s minus 2, so just going backwards, that's what we've got. And here, what we have got is e to the t times cos of 3t. Okay, so that is using the first shifting theorem and knowing what the Laplace transform is for cos of 3t. And that is the solution to the differential equation. So going back up and admiring the differential equation once again, here it is. It's a second order non-homogeneous ODE with some boundary conditions. And what we found is the particular solution to the differential equation. So the final answer is that the solution to the differential equation that also satisfies what we call the boundary conditions, f of 0 equals 0, f prime of 0 equals 1, is exactly e to the 2t minus e to the t cos 3t. Thank you so much for watching. As always, I highly appreciate it, and I'll see you guys in the next one. Cheers.